Hello! Today we're going to learn about how to solve another linear programming problem by using LpMinimize. Let's read the problem. So here we have the problem. Whiskas cat food, shown above, is manufactured by Uncle Ben's. Uncle Ben's wants to produce their cat food products as cheaply as possible while ensuring they meet the stated nutritional analysis requirements shown on the cans. Thus, they want to vary the quantities of each ingredient used. The main ingredients being chicken, beef, mutton, rice, wheat, and gel, while still meeting their nutritional standards. The cost of the chicken, beef, and mutton are 0.013, 0.008, and 0.01 respectively, while the cost of the rice, wheat, and gel are 0.002, 0.005, and 0.001 respectively, all in dollars. All costs are per gram. To meet the nutritional analysis requirements, we need to have at least 8 grams of protein per 100 grams, 6 grams of fat, but no more than 2 grams of fiber, and 0.4 grams of salt. So these are our constraints right here. So from this picture, we can see the 6 ingredients that make up a 100-gram can of cat food. So each ingredient contributes to the total weight of protein, fat, fiber, and salt in the final product. The contributions in grams per gram of ingredient are given in the table below. So for example, we could look at this chicken row, and we know that chicken provides 0.1 protein, 0.08 fat, 0.001 fiber, and 0.002 salt. Before I begin the problem using the different syntax of PuLP, I do want to turn your attention to code that's already in here. So the key problem data, so ingredients, a variable right here is a list of the 6 ingredients. And associated with that are the costs, which is going to be in a dictionary, and the different percentages of protein, fat, fiber, and salt. So neatly here is a dictionary with the keys being the ingredients and the values being whatever value is associated with that dictionary. Along with that, I went ahead and already wrote the import statement using all functions from PuLP. So first we need to create the prob variable. You can name it whatever you want, but I will name it prob, and we'll create a new cell here. We'll create some more cells. We create the prob variable to contain the problem data. So could go ahead and run that. Sorry, I forgot to run this function right here to import PuLP. So to do that, I'm just going to go ahead and run all the cells. Alright, good to go. So variable prob, like I mentioned before, it's not important. You can name it whatever you want, but it's created using the LP problem function. It has 2 parameters, the first being the arbitrary name of the problem, which is a string, and the second parameter being either LpMinimize or LpMaximize, depending on the type of linear programming problem that you're trying to solve. And specifically here, it doesn't allow any spaces, so I went ahead and put underscores between each word. Now let's define the reference variables in the problem. So I'm going to name it ingredient vars go ahead and run that. So sorry, I'm gonna change it right here, uppercase. The problem variables ingr underscore beef and then underscore chicken, etc. are going to be created using the LP variable class. So it has 4 parameters. The first is the arbitrary name of what this variable represents, which in our case is ingr. The second is the lower bound on this variable. The third is the upper bound. And the fourth is essentially the type of data, discrete or continuous. We didn't specify anything as a third parameter. So this is the lower bound right here, specified as 0. So since we didn't specify anything, there's no upper bound. The options for the fourth parameter are LP continuous or LP integer, with the default as LP continuous. So here, since we didn't specify it, it defaults to LP continuous. A dictionary ingredient vars is created which contains the LP variables with their defined lower bound of 0, as mentioned before. The reference keys to the dictionary are the ingredient names, and I'm going to just show you. I'm going to run it so you can see what I'm talking about. So here we see the dictionary. We see the ingredient as the key, and the value is going to be ingr underscore whatever the ingredient is. So I'll go ahead and I can leave that in there. I'm not going to delete that. Now we have to add the objective function. The objective function is just the cost of each ingredient multiplied by the decision variable, and for all these values to be summed. So let's add that objective function and utilize a list comprehension to make that happen. Went ahead and ran that. So the variable prop now begins collecting problem data with the plus equals operator. The objective function is logically entered first, with an important comma at the end of the statement and a short string explaining what this objective function is. So that's a string that we included, indicating what it is. Since costs and ingredient vars are now dictionaries with the reference keys as the ingredient names, the data can be simply extracted with the list comprehension as shown. LpSum is a function from the PuLP library that calculates the sum of a list of expressions. So just to show you, I'm going to go ahead and print it. So here we have the problem. It shows the string, the whiskers problem, and we're trying to minimize it as stated up here. And the variables we have listed here, ingr beef, chicken, all the way to wheat, and it shows that it's continuous. But up here, we added the objective function. So it is multiplied 0.18 for beef. So if we go up right there, that's the cost, and it's multiplied by each decision variable. So this is going to be our objective function. So 6 ingredients, 1, 2, 3, 4, 5, 6. So after the objective function is entered, the constraint is logically entered after this, with the comma at the end of the constraint equation and a brief description of the cause of that constraint. So I'm gonna create more list comprehensions similar to the objective function, which they're each given names describing them. So I want to take your attention to the problem up here describing the constraints. So the constraints are these nutritional requirements. So we need at least 8 grams of protein, 6 grams of fat, no more than 2 grams of fiber, and 0.4 grams of salt. There may look to only be 4 constraint equations, but all the ingredient percentages must equal 100, so that's our 5th equation. So let's go ahead and type out the constraints. Just to make it easier, I'm going to copy and paste for fat, fiber, salt. Change the values. Oops. Alright, everything looks good. So 1, 2, 3, 4, 5 constraint equations. And just to show you, let's go ahead and print it out. Percentages sum. And here we have everything from before, but it says subject to, and these are our constraint equations. 1, 2, 3, 4, 5 constraint equations as described from what we wrote up here. So greater than or equal to 8 grams of protein, 6 grams of fat, less than or equal to 2 grams of fiber, and 0.4 of salt. So it looks good. Now we have enough to solve the problem. So we can go ahead and run this prob.solve, which solves it. And previously mentioned in the other video, 1 indicates an optimal value. So we found an optimal solution with the objective value of 0.89 cents per can. So it's 89 cents, which is the minimum value needed to meet the nutritional requirements. But there's a different way that we can show this one. So the results of the solver call can be displayed as output to us using the LP status function, which can be one of not solved, infeasible, unbounded, undefined, or optimal. LP status is a dictionary, so its input must be in square brackets. So let's print out the status. So here we can access LP status, and it shows that it's optimal. But what if we want to find the percentage of each ingredient in the can? We can use a for loop to cycle through all the problem variable names and extract the value using the var value function. So let's go ahead and create another cell. So neatly, it will loop through the variables and it'll give the name. And here we just use a print statement of equals, and it'll give us the value here. And name and var value are properties of the object variable. Let's go ahead and run that, and here we see the percentages of each ingredient, and it looks like mutton has the highest percentage with 50% of the can being mutton. So we're able to see the percentages from each ingredient. So even though we already saw the total cost of ingredients, we can use the value function to extract the value for the total cost of ingredients per can. So just to make it look better and to solve the problem, so neatly written, total cost of ingredients per can, 89 cents. So that's a wrap for this video. Hope you learned something, and thanks for watching.